Okay, let's start today by going over the quiz, and then hopefully we'll have enough time to do Lab 5. Are the lights okay? Do you want to turn the lights down more, or is that okay? More, or is it okay? Huh? It's okay? No comment? Okay, when the code in Figure 1 runs, what does it print? And let's do that. So once again, we basically have to read this, right? And we have to make mental notes of what are the variables and what are their current states as we walk through execution of the code. So we start here, we declare a variable I, and we set it to 1. So we make a mental note of that. And we enter into this loop, and inside the loop we print something. So it looks like we'll be printing a lot. And there's a condition in the loop. The condition is that I is less than 128. So as long as that's true, we'll do what's in the body of the loop. So when we get to this point here, we need to print the result of evaluating this expression. And so I is currently 1. Now we take 1 minus 1 is 0, so we print 0. We're going to print a 0, and then a space. That's what this is. And then we'll compute 2 times I is 1. You have to keep in mind that this expression here was evaluated and became 2, but it did not modify the state of I. It's just an expression. It's not an assignment to I. This is an assignment to I. This statement, the result of that statement is normally a modification to the state of I. So I is currently 1. We do 2 times 1, that's 2, and we store it into I. Now I is 2. We compare 2 to 128. It's less than 128. And so we execute the loop. And we need to evaluate this expression and print that. That's 2 minus 1. That's 1. Or print 1. And then we take 2 and multiply by 2. I is 2. And we get 4. So I is now 4. We're at the bottom of the loop, so we resume execution of the loop from the top. We have to check the loop condition. So I is now 4. 4 is less than 128, so we will print 4 minus 1, which is 3. And then 2 times 4, which is 8. We store 8 in I. 8 is less than 128, so we print 8 minus 1, which is 7. 2 times 8, which is 16, store that into I. So you got to keep it straight mentally, you know, what is in I and what is printed. Those are two different things. So I is 16. 16 is less than 128. We print 15. 2 times 16 is 32. 32 is stored in I. 32 is less than 128. Print 32 minus 1. That's 31. 2 times 32 is 64. Store 64 in I. 64 is less than 128. So we print 64 minus 1, which is 63. 2 times 64 is 128. 128 is not less than 128. So we're finished. And that's the result. All right, let's do the next one. Suppose that k is an integer variable. write code that prints good when k is either negative or equal to 100 and bad otherwise. So we have a k. You can declare it, you can input it if you like, but the problem is that you suppose that k exists, that it's an integer variable. We don't know what its value is, but it's there. So we use it. So if k is either negative, in other words, if k is less than 0, or k is equal to 100, in this case, print good, otherwise print bad. Oops, sorry. There it is. If k is negative or equal to 100, there's the expression. This is k is negative. This is the symbol for or k equals 100. And once again, on the quiz, things like this are fine. This is okay. That's not a problem. All that stuff. That's good. So I wanted you to show me that you understand how to use a conditional. Okay. Problem 3. How many times does the body of the for loop run in the code that appears in figure 2? See this expression in here, I plus 1, that's an expression, it's computed, it's sent in to cout. It does not change the state of I. So that's something we can basically discard that. It doesn't do anything. But we want to know how many times it runs. So we look at here, we set I to 0, and then we have a condition that involves I, and then we increment I. So we want to know, how many different states does I take on? That's how many times the loop runs. If we start at 0 and we stop when we get to 901. We start counting from 0 and we get to 901. That's 901 times. See, we're starting counting at 0. And we're ending at 9. Let's suppose we started counting at 1. This is, by the way, this is the common expression. And this would be perhaps how people normally think. They start at 1, and they end at, and by the way, we could just put the 901 in here. That's what k never changes. If we started at 1 and stopped at 901, we would have done the loop 901 times. But we didn't stop at 901. We stopped at 900. We don't admit 901 as a value. So we stopped 1 before 901. But we didn't start at 1 either. We started at 1 before 1. We started at 0. So this is an example of a one-off error. If you got this wrong, and many people got this wrong, this is a point that I tried to make several times in lecture, that there's a one-off problem in computing. And this is an illustration of the one-off problem. If you got it wrong, it's an illustration of the one-off problem. This is a very common and pervasive problem in computing. And that's the theme and the reason for this question on the exam. You have to think very carefully about how to understand these types of automations to avoid the one-off error, the one-off problem. All right, let's take a look at 4. Rewrite the code in figure 2 so that it uses a while loop rather than a for loop to accomplish the same output. There's figure 2. So we want to use a while loop. So the initialization of all initialization needs to be taken out and placed before the while statement. And the while statement takes, well, the condition, the keyword while is followed by parentheses with a condition in there. That's the loop condition, which is I is less than 901. And then at the bottom of the loop, we need to do what was done at the bottom of the loop in when we used a for loop, which is to increment I. So that's just a matter of rearranging things. So the reason for this problem is to understand the essential equivalence between a for loop and a while loop. Question? In figure 3? Well, you don't need to increment I. That's you could do a different operation. Like for instance here, we're incrementing I because that's what we want to do. But we could have done something else. We could have done that. We could have multiplied I by 9. So just because we incremented I, that suited that problem. But for a different problem, we have another operation that we need to perform. Yeah.
I got marked down because I didn't define shape. I just put 901.
Show me if you have a. I mean, it's likely that we made some mistakes grading a paper. I sat with Jaren and we graded all these papers, and it took basically forever. And 10 problems, 55 submissions. So we're bound to have made some mistakes. So if you see a mistake on your paper, please see me at the end of the class today, and then I'll check it, okay? Because it's likely that we made several mistakes. Okay, let's go forward. When the code in figure 3 runs, what does it output to the console? Right. Well, here's another code reading problem. So we define a variable I, set it to 9, and then we enter into this loop, and then we print something. And that's what we need to do. What does it print? So there's only one print statement. This print statement is not inside the loop. It will not repeat. We're going to print one thing. And we're going to print the value of I. But we're going to print the value of I after it's modified inside this loop statement. So we have to figure out what does I become. And that's what we print. So set I to 9. Let's go into computer mode now. Let's pretend that we're a computer. And let's allocate memory to store a variable called I. Let's initialize it to 9. All right, next statement. It's a while statement. Actually, this whole thing is called a while statement. And it has a condition. Before we do the body of the while loop, let's evaluate its condition. I is 9. Is 9 less than or equal to 99? Yes, it is. Let's add 11 to 9. Well, now this is going to get complicated, so we better store what we think I is. So right now I is 9, so if we take I and add 11, we're going to get 20. And we'll store 20 back into I. So we're going to change I to 20. And then we hit the bottom of the loop, so that means we come back to the top and evaluate its condition. We compare 20 to 99. The condition is still true. So then we execute the body of the loop. We take what's in I, which is 20. We add 11. Now we have 31. Store 31 in I. Come back to the loop condition again. 31 is less than or equal to 99. Let's add 11 again. That's 42. 42 is less than or equal to 99. Let's add 11 again. 53. Add 11 again. 64. 75. 86. 86 plus 11 is 97. 97. So when this computes to 97 and we store 97 in I, the loop condition is still true. So that means we come down here, we add 11, and we're going to get 108. We check the loop condition. The loop condition is now false. And so we print I, which is now 108. Okay. Let's look at 6. Right, when this code runs, what does it print? Is there any loop in there? No, there's no loop. There's a conditional. There's a condition in here, an if statement. There's two of them, and it's not if else. There's just two if statements. So if the first if statement is true, then we print alpha. And if the second if statement is true, we print beta. So if both are true, we print both alpha and beta. If neither are true, we don't print anything. So let's see. I is 1, j is 2, x is a double. I and j are ints. Okay, so, well, this is an exercise about remembering the difference between integer division and floating point division, and also basic understanding of how to read code. So I divided by j, when I is 1 and j is 2, is 0. Because that's integer division. We divide, we toss away the remainder, so we get 0. So 0 is not greater than 0. We do not print alpha. X divided by j. Well, x is a floating point number. It's a double precision floating point number. And therefore, the compiler interprets the slash as floating point division. So we do not throw away the remainder. We keep the remainder. So we get 1 divided by 2, which is 0.5. 0.5 is bigger than 0, so we print beta. All right, let's look at number 7. 7 refers to figure 5. When the code of figure 5 runs, what does it output to the console? So we set I to 2, j to 2. Then we have the pre-increment. And here we have the post-increment. So the pre-increment means you do the increment first and then use the result of the expression. Here we will increment I becomes a 3. And j is still 2. So I becomes 3 here. And then we use the result of this expression, which is 3, and send it to Cout. So it's going to print 3. Then it's going to print space plus space. Oops. And then it's going to, we got a post increment there. It's going to use J, and after it uses it, it's going to increment it. So let's use J. Well, J is 2. And let's send 2 into the output stream. So we're going to print 2. Now we finished using J. Let's go ahead and increment J. J is now 3. And then we print a space and then equals what? Question mark, new line. And then the next line, it doesn't equal space. And then we need to evaluate this expression. Well, that's 3 plus 3. That's 6. So we print 6. And then we print a period. Yeah. This is not assignment? It's not assignment, that's correct. Although you could, it modifies the state of J. It does modify the state of J. Yeah. That's right, that's not assignment. And that doesn't modify the state of I. But this does. This modifies the state of J. So the plus plus operator does modify the state of the variable it's attached to. So in that sense, it is, you could think of it as an assignment. It's not the assignment operator, but it does assign to J. It modifies J. We covered this in the practice quiz questions. You know, this should have been clear. This, you know, this question here is not a trick at all. This is very similar to the, is it the assignment 2 problems? So, you know, if you were confused about how this works, it should have been cleared up in the assignment 2 problems. Okay, write C++ code that computes the sum of integers 20 through n, where n is an integer strictly greater than 20. All right, we need to compute the sum of integers 20 through n. So we'll use a, you could try to figure out a formula for that, or use the loop. And I want you to use the loop. So we're going to have, we know exactly how many times we run the loop. We're going to run it n minus 20 times plus 1. Or maybe not the plus 1, depending on how we write it. So we need a variable to accumulate the sum. We'll set that to 0. And let's range through the values 20 to n. So this is not correct. Let's range through the values between 20 and n. and add them into the variable sum. That's it. You don't need to print it. If you print it, that's fine, but I didn't ask you to print that. Just compute it. Okay, let's do the next one. Write code that prints every even number between 100 and 1000 inclusive. Back to number 8. No, this is just the condition of the problem, the assumption of the problem. N is an integer strictly greater than 20. In other words, you can assume that when you write the code, N will not be 20. N can be 21, but N cannot be 20, N cannot be 19. It's just the assumption that you make when you write the code. So I'm telling you what assumption to make. I'm saying that that N is an integer. N is a given integer. And that integer is strictly greater than 20. You don't need to enforce that in your code. You could if you wanted to. You could say, you can say cert N is strictly greater than 20. You could do that. That's fine. It's good. But see, you don't have to write any code that sets N or does anything with N. You just assume that it's strictly greater than 20. Is that okay? Okay. Print every even number between 100 and 1000. We could use a for loop or a while loop. And every even number. There's so many ways of doing this. I'll do it with the for loop. We'll start at 100. Well, I is less than or equal to 1000. Add 2 to I. There it is. There's one way to answer the question. So see, in the loop, we're not incrementing by 1. We're jumping forward by 2 values. Just add 2 to I. So that'll give us every even number. So there's other ways of doing this, right? You can imagine there's many ways of expressing this and writing it down. Any questions on that? Does anybody want to see it done in a different way? Okay, let's take a look at how it would be written with a while loop. So, with a while loop, let's set a variable to 100. And while I is less than or equal to 1000, let's print the I. And increment I, or add 2 to I rather. So you got to check, make sure, does it print 100? Well, yeah, it does. We set I to 100, prints it. Does it print 1000? Well, after it does this operation, it reaches 1000. This is still true. and therefore we will print 1,000. And then we will make it 1,002. Now this is false, and we will not print 1,002. You want to check the two extremes, you know, the starting times and the finishing time. Make sure that you got those right. Okay, write C++ code that prints 100 random integers where each integer is between 0 and 99 inclusive. Use the rand function with the modulo operator. That's a hint. We want 100 random integers. So we just need a loop that runs 100 times. Let's do that. This would be the standard expression, which is not intuitive to beginning programmers, but which is expected in professional programmers. Okay. We get a random value. Let's call it k by calling rand. But that's too big of a number. The full range is large, so we need to divide by 100 and just print the remainder. Once again, this expression here, this means take k, divide it by 100, and throw away the value, keep the remainder. Throw away the quotient. And so that expression that's evaluates to the remainder. It's going to be between 0 and 99. It'll never be 100. Now, when you divide by 100, you're never going to get a remainder that equals 100. I mean, otherwise it's, you know, you got one more. The quotient is off by 1 now. Okay. Any questions? No one? Yeah?
If you do C out and then you just do rand mod and then a number, does that...
What's the number?
I put 99.
Yep, that's wrong. That's 0 to 98.
Okay, so
That'll only do 0 to 98. You won't get 99. Does that make sense?
Yeah.
Okay. Okay, let's go to look at, I think it's lab 5, right? Did we do this one in lecture? No. Okay. So random colors. Reorganize your code in the solution to exercise 3. Is there anybody who did this? And I could just check out your code and fix the problems that you're having. Is anyone stuck? You want to do it? Huh? Well, actually, if it works, that's fine. We can do that. I'll save time. All right. So let me bring up your solution, and let's see. I'll go to the. You're going to need to spell your name for me. Oh, Andrew. I remember. Andrew. Hold on there. Andrew Brinker. You're right there. All right. This one. All right, let's look at Andrew's solution. And we have, let's start looking at the main function. And what we're going to do is we're going to basically reorganizing what?
You want to make it so that the thing from the assignment uses a function instead of just everything being inside main.
Oh, assignment 1, right? Assignment 1. Let's see. So let's look at assignment 1 code first. Do you have assignment 1? Can we look at that? Is that all right? So here's assignment 1. Look at assignment 1. Everything is in main. And to get the job done, right, we print the heading of the HTML document here. And then we enter into this loop that runs 100 times, and it prints 100 random values, right, with HTML markup around it. And then at the very end, we print the ending markup in the HTML file. And this is a little bit hard to read and to manage because we've got one for loop here, and then we have another for loop on the inside. It makes it a little tougher to manage this code. By the way, the indentation here looks pretty good. So he's got the function here, then everything that's inside the function block is indented. So everything that's inside main gets a single indent. And one of the things inside main is the for loop. And the for loop, everything within the body of the for loop gets an additional indent. And this style of programming, I mean, which is the generally accepted style, is required in this class. You must use indentation to show the logic, the organization of your logic. So when there's a multi-statement block like a for loop or a while loop or an if condition, that you need to indent the contents of that block of code to show that dependency. This code is dependent on the condition of that if statement or the condition in the while loop. So inside this for loop is a declaration of a string here and then another for loop. So the problem was to reorganize the code. So we don't want the code to do, we don't want it to do anything different. We just want it to, we want it to be coded differently. We want to use a function. So we want to write this function so that the function generates a random color string. And by doing that, we can remove the nested loop that we have. And removing nested loops makes code usually much simpler to read and to maintain. So let's take a look at how Andrew did that. We still have this loop, but we print, we print the strings that comprise the top part of the HTML document. We print the strings that comprise the bottom part of the HTML document. And then inside here, we print the 100 list items. It's called li, it's a list item. So we generate a random color string using the function getColor. So we define a function called getColor. We call it, it returns a string, a color string. And then we can use that color string in where we need it here, which is in two places. That means we move all of this business in here, so we still have this line. That line is right there. Color equals, this is where we're declaring color. Here, Oh, we're calling it color string here. We're declaring the color string there. But we initialize it to empty string, and down in here we end up setting the color string, right, through this logic. And so at the end of this for loop here, at the end of this for loop, this color string value is what we need it to be, and then we use the color string value here. But what Andrew did was he renamed it. He's just calling it color now instead of color string, but he uses it in the same way. So that inner for loop is now moved into this getColor function. So we say, we need a color string. Call getColor. Use the string. Do you see how much simpler it is to read this part of the code? So the logic to generate the color string is done inside this function. Here it is. We declare color string here, initialize it to, this is just the code that's in this part here. This is just this stuff here, cut and paste it into the getColor function. Any questions on this? Yes, question.
When I kind of just scribbling, so I'm looking at my notes. But I put the string color of the empty string into main. Does it have to go in the?
Can we look at your code?
I haven't revised it.
You haven't committed it?
I just have the notes.
Oh, okay. So you're putting inside main.
Yeah, pretty much. I'm just gonna call color back in there. Like I called it color.
We call it like this. Is it different than this?
A little bit.
How would?
Not very different. Just
Why don't you let me, because it's hard to talk about it. You know, let me take a look at your code later on. Okay? Yeah.
Are you going to show us later how to make all this work much more simple without, like, it takes up like that much space
Yeah.
to do that work? Is there a way to make it shorter or more simple?
You can't make it much simpler than this. You can use tricky code to make it more compressed, but then you have to, you know, comprehend the trick. This is very straightforward, easy. Yeah, it takes a lot of space, but and you could probably get it down to a few lines, but you're going to use very sophisticated, tricky code, and yeah, I don't think that's necessary. Yeah.
Switch statement work?
Yeah, you can use a switch statement. Did the book cover switch statements, right?
Yeah,
Yeah, so you can use a switch statement, but I don't think that's any easier. And switch statements in C++ are error prone because people forget to put the break statements in there. Or the compiler allows the break statement to be omitted. So switch statements in C++ are not well designed. The switch statement was fixed in the C# language. The C# language requires a break statement. It doesn't allow what's called I forget what they call it now, when you pass through one case statement to the next. So switch statements in general are a little tricky, and but you could use it here as well. Yeah. I'm taking Lab 5's late. You know, if you could get it in tonight, that'd be great. So it's okay to submit Lab 5 late. Because I noticed a lot of people were kind of falling behind on that. So, and I didn't cover the material lecture yet. So Lab 5 is okay to be late, but don't make it too late. If you can get it in tonight, that's good. Yeah.
So are we going to go over lab 6 on Wednesday?
Yeah, we'll go over Lab 6 on Wednesday. All right, let's take a look at this isPrime function. Did we do isPrime? Did we do a problem on prime, determining whether things are prime?
Exercise exercise 2 lab 4. Yep, exercise 2 lab 4.
Exercise 2, Lab 4.
Yeah.
Oh, here, right. So Um, is there someone who wants to show their is prime function, exercise 2? Anybody, any volunteers on this? From the repository? I will criticize your code, so prepare yourself to be criticized. Huh? Yours? I'll go back there. Yours? Who? Volunteer?
You can use mine if you want.
Okay. Is it running? It doesn't have to run. You can submit your code for lecture without having it run. We'll fix the problem.
Michael_Pratt.
Okay, hold on there. Is it Pratt?
Yeah.
Oh, we got everything. All right, Lab 5, Exercise 2. So here's the is prime function. Is prime, it takes an integer n, decides whether n is prime or not, and then returns true or false. So the return type is bool. Okay, so that's what this does. This logic should decide whether n is prime or not, and then return true or false accordingly. And then what the main function looks like is just a bunch of test cases. And that's good. I'm glad to see this one in here. That's the one that was a lot of people were getting stuck on here. And let's see. I don't know if I can build this. Let me see if I can build this. I cannot build this because I need a project. Let me try making a project. In Visual Studio, in this class, we create projects that are Win32 console applications. All right, let's see if this builds. Looks good. So we have these test cases in here. We pass in 2 to is prime, and that should return true. 2 is prime. So we assert that this, basically the assertion function takes an expression that evaluates to true or false. And if the expression evaluates to false, then the program shuts down and the system reports a line number where the failure occurs. 3 is prime, 4 is not prime, that's why we negate it here. 5 is prime, 9 is not prime, so we negate it here, and so on. Those are nice test cases. Let's see if it runs. So we look in the console window. Oh, we fly right through there. So I'm going to put a breakpoint right there just to stop execution. And all tests passed. Good. If you had an error in there, let's take a look at what if we had an error. Let's suppose is prime 4. Let's suppose we put it in like that. It should fail, right? 4 is not prime. Let's see what happens when we run that. I'll put a breakpoint there again. There it is. So we get a failure here. Assertion failed. Is prime 4. It even gives the line number, line 23. So that's convenient. So, well, in this case, the test case is not good, so we'll fix that. So this logic in here, we looked at this in an earlier problem, right? Was it lab 4, whatever it was. I don't think I need to go through. Do you want me to go through this again, what this is all about? I think I'm going to skip that because we're running out of time. Exercise 3. In exercise 2 of lab 4, you wrote a console application that computes and displays all the prime numbers between 2 and the number entered by the user. Use the isPrime function to do that. So watch this. I'm just going to modify this. So what the user enters a number, right? So it's so call it n. The user enters a number. Then what we want to do is print all the prime numbers between 2 and n. I'll use I. Oops. This should be I is less than or equal to, no, I'm going to do less than n. So we're going to use our isPrime function. Pass in I. If I is prime, then let's print I. Let's run that. Syntax error. Almost out of time. Oh, what happened? Oh, I got to put a number in there. Okay, say 99. Oh, there it is. 2, 3, 5, 7, 11, 13, so on, 97. That's how we do. That's how we use the isPrime function to do exercise 3. Okay, that's it. I'll see those in lab who are coming to lab. If you have any questions about your grading, the grading that we did on your quiz, please show that to me.